Now the next speaker hitting the stage is Taneli Korhonen. Taneli is a robotics and ROS developer at Karelics.
Taneli, in his speech, we are going to learn how to create proper ROS2 multi-threading programs while avoiding deadlocks. His talk is entitled Using Callback Groups in ROS2. Hello, Taneli. Are you ready for the speech, for the presentation? Hello?
Hello?
Yes, I can hear you. Are you ready?
Yes, I'm ready. Good to
Excellent. So the audience. Go ahead.
Okay. You somehow cut out, so all right. Yes, hello everybody. Hope you're doing well and having fun with the ROS Dev Day so far. So my name is Taneli Korhonen. I'm a mathematician and a ROS developer at Karelics. And in this presentation, I will be telling you about callback groups in ROS2. So this topic is something that we at Karelics stumbled upon a bit over a year ago now, I think maybe a year and a half ago, on our kind of last stretches of migrating to ROS2. And it caused us a little bit of a headache back then. So we ran into some bizarre deadlocks that took a while to figure out why they were happening. And because of that, I then ended up writing a blog post about these deadlocks in RCLPy to our company blog and also to ROS Discourse. And that gained a little bit of traction and turned into a page also on the ROS2 documentations. And so in this project, I will be kind of continuing this topic and trying to present this properties of callback groups, how to use them, also how not to use them, and why you should care about them, with maybe a little bit more examples than in those posts. And about the examples, I will be using RCLPy or Python for demonstrations, because it's maybe a little bit easier to demonstrate with. But for those of you who may be interested in the C++ side of things, the properties that I'll be showcasing are essentially all the same on RCL-CPP. And this project also contains examples in C++, the same examples you can find in CPP as well. So if you're interested in that, then feel free to look over those on your own time. All right, I guess let's get going, and we'll start with a little bit of theory, something that we need to know when we even talk about callback groups. So first of all, you need to understand a little bit about executors. So almost all the work in ROS2 nodes is somehow run through callbacks, or happens in callbacks, and callbacks are executed by executors, and there's two main types to choose from, and those are the single-threaded executor and multi-threaded executor. And if you know anything about threading, there's an obvious difference between those two, and that is that the multi-threaded executor can execute more than one task concurrently, while the single-threaded one always needs to finish the previous thing that it started before it can start anything new. And when we're talking about callback groups, we will be focusing on this multi-threaded executor. So for this, ROS2 offers callback groups as tools to control the execution of the callbacks for each executor. And there's again two choices. There's a mutually exclusive callback group and a reentrant callback group. And the difference between these is that all callbacks who belong to the same mutually exclusive group are such that you can only execute one of them at a time. You can never execute two of them concurrently. Whereas on the reentrant group, you can execute callbacks in whichever way without any restrictions. And then also, if you have callbacks in different groups, then you don't have restrictions again. So it's essentially like they were in a reentrant group. Okay, so now with this basic theory down, let's go to the examples. And before we start running them, I will just quickly mention that we're using Python and the workspace is built with Symlink install, so everything should work without needing to rebuild. But it seems that the Symlink, at least on this virtual environment, is a little bit finicky sometimes. So I have provided here you with commands to use for building the workspace. If it seems like some example is not working correctly, just run this, or maybe run it in a separate terminal just to build, and then source everything again, and it should work. And I think I will be also doing that myself just in case when we get going. So to the first example. So this is about allowing parallel execution. So we will see how we can use callback groups to either prevent or allow parallel execution of callbacks when running a node with a multi-threaded executor. So to check this, let's open the IDE if you haven't already. We'll try to make it a little bit bigger so that it's easier to see. And open the ROS2 workspace. And in there you will find a file processor package. And under that, you will find a file processor.py. Okay, so looking at this file, let's see what it has. So we can see that it's a fairly simple ROS node. We have two services defined here, one for processing videos and another for processing images. And then if we look at what these do, they're rather simple. These are kind of mock services trying to simulate some real work. So processing videos, we just download a video and then process it and then return success afterwards. And processing images is a little bit faster than videos, so we have simulated the work here by just sleeping a little bit. So processing a video takes about 2 seconds. Processing images happens almost instantly. And because there's this big difference between how long the processing takes, we have chosen to run this node in a multi-threaded executor in the hopes that maybe we can process several images while waiting for one image to process, assuming that we have spare resources, of course. So that is it about that. And then we also have a file with some clients for this. So if you open processfiles.py in the same package, we can see that we have clients for both services, processing videos and processing images. And then we have some functions for sending these requests. So here we just send a call to process some video or an image, and then we have callbacks for getting the result when it's ready and printing what the outcome was. And also in here, well, here we're just spinning it with a simple default executor. And but okay, we are not actually sending any requests yet, so let's add that so that we have something to try. So let's copy these lines and add them here in the main before the spinning. And so that should do it. Now we're sending a request to process one video, and then waiting a little bit, and then sending a request to process an image, and then we will spin to get the results. Okay. So let's run this example. We will need a couple terminals for this, and the second one and I will get a third one for potentially building the workspace. And I think I will start by actually doing that just in case, to make sure that everything is up and running. Okay, so let's run the example. I have here commands for it. So first sourcing the workspace and then running the file processor on one terminal. And then sourcing and running the requests. Requests in a different one. And let us see what happens. All right. So what we expected would of course be to have the okay, something is not okay. It looks like for some reason the processing of the video didn't work quite. Let's try the rebuild one more time, and then let's run the node again.
Maybe removing the directories of the compilation and compiling again.
Yeah, that might be what I need to do. Okay, let's try that. So I should remove these two, I think. And let's make a fresh rebuild. Now it will take a little bit longer, but I think it should be fine. All right. Source and run. Still not working. Let's double check that I haven't accidentally changed anything here. I don't think that should be the case. No. No, it should all be okay. Okay, I'm not sure why it's not, why the video service isn't found right now. I did have this problem sometime before, but it got fixed by just rebuilding. Let me try one more time to rebuild. Maybe in this other terminal.
Yeah, and open a new terminal. Maybe it's corrupted already.
That's true
Open,
also.
Open another.
Let's just make all new terminals.
Yes, they come for free, so you can open as many as you want. these things happen as we are in live and doing the demonstration live. So
this is the classic demonstration effect.
yes.
That for some reason the video is just video service is not working at all.
Okay.
But okay, maybe I will.
Can we skip this example and move to the next one?
Yeah, I can.
You decide, Taneli.
Of the outputs, and so yeah. So I have the screenshots of the expected outputs. So let's just go with these.
Yeah.
So what should happen here? And I'm not sure now why it's not working. Might be that I just need to, fiddle something in here. But what should happen is that the video now, we get the request for processing the video, and it actually kind of blocks the processing of the image. So while when we used the multi-threaded executor here, we wanted the video to kind of process, or the images to be processed in the middle of the video processing, but that doesn't actually happen. So the image will need to wait for the video to process. And so now let's think about why this is the case. And why this happens is that now, in order for the executors to do their work, every callback needs to actually belong in some callback group. And this is why the nodes, ROS2 nodes, have a default callback group set up to them, and that callback group happens to be a mutually exclusive group. So because we have not set any callback groups here, neither of these service definitions contains any information about callback groups. Both of these services will run in the same mutually exclusive group. And what that causes is that the video processing blocks the image processing. So when the video processing starts, we get a task to run that callback. And then while we're processing that, we get the request to process images, but that execution will have to wait. The task gets created, but it will have to wait for the video processing to end before it can actually start. And there's a couple of ways we can fix this. Let's now see if the fixed version works. So the easiest way to fix this is to just change our callback group setup so that these callbacks will be in different groups. And so this is what it should look like. So we set these into different groups, and then they will not be blocking each other. So this video callback starts, and when we get the request for the image callback, because it runs in a different group, it doesn't get blocked by this, but it can execute immediately. And then the expected output would be so that if we compare to here, we will see this image actually finishing before the video on the client side, and also on the server side, these couple lines will move up to be in the middle. So let's give this a try. We will need to import the callback group. So add it here to the top of the file processor.py in the imports. And then let's change the video service so that we set it with a callback group. So just add this one line here at the end of the video processing. And still double checking that this looks good. It does. So that should be okay. All right. And now let's, once again, I think I will go ahead and rebuild just in case, because it didn't work before. And then rerun. So that's the request side, and this is the processor. And let's see. Still, for some reason, the video service is not found. Okay, well, good thing that I have this setup here. So this is what should happen. Yeah, so here's what should happen. So we should the image should be finishing first, and then the video finishes when it's ready. And so that should be all good. I just got an idea. Let's try something a little bit weird, even though I think this shouldn't be the case. Let's change the name of that a little bit and just try rerunning. No, didn't help. Worth the try. Okay, well, then there's a second way to fix this also, and that is by using actions. So now this video processing takes a little while, so it actually makes sense that it might be an action. And actions have a kind of a nice feature in that their execute callbacks are actually not blocked by callback groups. So if we change this video processing to an action, then we can just have it in the same callback group as the image processing, and it should be able to run in parallel with it. So let's give that a try. For this, we will need to add some new imports to the service node. So we will need to import action server and the message type for processing the videos, the action message type, that is. And then we want to, of course, create an action server. Let's just add it here below. And then we, of course, need this execute callback for the action server as well. And now, if you compare this execute callback to the processing video callback, it's essentially just the same. The only difference is that this is written for an action while this was a service. And to send requests to it, we of course need an action client. So let's add that to the process files.py. Again, we want to import some action entities and create a client. And there is an action client. And then we want the functions for sending the goal. So me paste this, and then I will explain what it does. So here we just send a goal to the action server, and then we get the so then we get the response, check that it was accepted, and then we wait for the result and again print that the video was done. And then as the last thing, we of course want to now send the request for the action instead of the video. So let's switch these lines. Let's just comment out the service request. And let's see what happens if we try this. Running the file processor and sending requests. And looks like also the action is being stuck for some reason. One more time, try and no. Doesn't look like the video stuff is just not working for whatever reason now. All right, well, I will not stay on that for too long. Let's see if that fixes itself at some point. Let's just go on.
And what about the initial setup when you started the ROS jet?
Yeah, what about that?
So maybe you can go back to that one, set up, and then just go very quick through the steps. Because I'm pretty sure it's something that in all those steps, there has been a small error somewhere now. Because this is working. But I don't know. I'm suggesting maybe do an undo here for everything.
I can try it, of course. I don't think it's going to make a difference. But,
okay. Then no, it's your presentation then.
Well, let's give it a quick try.
Okay.
We are not going to need this action example actually after that in any case, so this should be okay. Just getting rid of all of these. We just try with a fresh terminal one more time.
Yeah, can you try to compile in one terminal, but then execute in a different one?
I can, of course.
Yes.
Let's try that.
But wait. You have to, if you do that, you need to remove the build and install, sorry.
Oh, again?
Yes, okay, because then we don't know what's happening there.
All right, let's try that one more time and see what that gives us. This is again something that I did run into also earlier, even like around the submission time, but it always got fixed by just building again.
Compiling, yes, I remember we were testing this.
Yeah, we
together.
We talked about this. So it always got fixed by just recompiling and maybe taking a new terminal. So I'm not sure why it's now being such a problem. But just give it one more chance and then move forward.
Mm-hmm.
No, looks like the same result. For whatever reason, the video processing seems to be just stuck now. But
okay, we cannot dedicate the time now to debug this.
Let's not. But this seems to have been, and I have not seen this like when I've been running these examples locally on my own machine. It has never happened, so I'm not sure what's up with that. But let's continue. So our second example, second use case for callback groups, if you will, is protecting resources. And so in here, if you think about how the mutually exclusive group worked before, it's kind of like a lock for callbacks. And that is essentially what it is, actually. So this, if we take a look at our next example, so now we want to open object storage package, and there's an object handler.py, and this node has essentially keeps track of some set of objects, which in this case are just ROS messages, simple ROS messages that contain an ID and a name and position. And we have implemented here the standard cruiser operations for sets of objects. So you can send a list of objects to add or modify or delete. And then we are also simulating some real work that might be needed for some data processing by some sleeps here. And again, now motivated by the previous example, we are running in a multi-threaded executor, and we have also set these to run in a reentrant callback group, all of these operations, so that we will allow everything to run nice and smooth without getting blocked by each other. So let's add some default objects, just as we have something to work with. So let's add these lines here in the main before spinning again. So we're defining here 3 objects that we're adding, just IDs 1, 2, 3, and names the same, and some positions. And then we're calling the add once here, the add method once here in the main before we actually start spinning the node. So then we should have some objects stored already at the start. Oops. And all right, then for this one, we also have a helper script for doing the updates. So update objects.py contains clients for the add, modify, and delete. And here, these are, again, simple functions to just call from the main, which take whatever list of objects they are given and request either adding, modifying, or deleting that. And then we have a callback for getting the response and printing the objects currently stored, which all of these services return the currently stored objects. So let's add some requests. I'm trying to go a little bit quickly here to catch up some time.
Yeah, we are 10 minutes to go.
Yeah, that's what I thought.
And by the way, so the audience already spotted the problem. And
Okay.
it's a stupid thing is in the process files.py. So you have to indicate /process video instead of just process video.
That shouldn't matter, but let's do it.
Well, that's how they got it working. That's how they say.
Okay. Well, if it works, then good. Let's just add it there. This shouldn't affect anything. This is just a namespace or override basically, but maybe for some reason it does it here. So okay, good. Yeah. So okay, I'm not gonna be explaining what this actually does or is supposed to do, but if it worked, that great, good job, guys.
Okay.
And thanks. Okay, let's continue with our example here. I'm wondering if I should now rename all of these, just add the slashes everywhere just to be sure. Maybe it doesn't hurt. And it shouldn't hurt, so let's do it. Okay, so what we want to do, we want to first add a couple new objects, 4 and 5. Then we want to modify some objects, so the 4 that we just added and one of the older ones, and then finally we want to delete the couple last 2 of the objects, and we're sending all these requests in a quite rapid succession with some small waits in between just to give them time to process. So let's run this example and see what happens. So let's take our terminals here, and on the first one, want to run the object. Okay. And in the second one, we want to get the requests. I actually might want to make this a little bit bigger now because I think the output prints are quite large. Let's see what happens. Okay. Also looks like there was something not quite working here. So as expected, at least. So we got the add request and no, this is actually the one that we did before. So modifying got requested, delete got requested. This time the add didn't work for some reason. Let's try rebuilding again in a moment. Or actually first. Okay. Yeah, well, looks like the add doesn't work. I don't know why it is what it is now that the first thing that's defined doesn't work for some reason. That's the way it now seems to be. Well, here's exactly the second one. Well, again, let's not. We're running out of time, so let's try to get to the end.
Maybe you can just as before show the expected result, and then let's continue.
So yes, so what should happen is that we should still get some errors like we did here. Actually, pretty much the same errors, but we should also be getting this done request or add request, which is not now happening. And so some of the objects that we wanted to delete or modify are missing, and we get actually an incorrect set of objects at the end. So we would expect to get 3, we find 4, and the fourth one is not modified as it should be. So quickly thinking about what went wrong here, well, we're working with bulk operations, bulk root operations, so we should protect those against concurrent modification. But we failed to do it here when we were a little bit over-eager and set the reentrant callback group. So what happens is that the add does start first, and but then when we get the calls to modify and delete, those also start before the add can actually do anything. And it happens that the deletions happened first, and then we start modifying something that isn't added yet, and then finally we start adding stuff, but we have already tried to do some operations on things that weren't there, and then the modifying also happens so that we try to modify something that was already deleted before. And the solution to this is simple. So we just set a mutually exclusive callback group for all of these services to the same mutually exclusive group, and that should fix it. Then what happens is that this add will execute first, and then modify and delete will wait, and modify will get to execute second, and delete will execute the last. So let's give this a quick try. Again, now I'm not starting to not be very hopeful that this is going to start suddenly working, but let's give it a try nonetheless. Actually, we don't need this anymore, and then we just want to switch this callback group to a mutually exclusive one. And let's see what happens if we just try rerunning this. Yeah, again, the add is not working. I'm really hoping that it works for you guys, all doing this at home. But for me, for some reason, it's not working now. But what should happen is that we get rid of the errors, and the add finishes first, modify second, delete last, and we get the expected result at the end. And now, as a really quick 10-second side note, this solution is essentially the same as just running the node in a single-threaded executor, and which one is preferable for any particular case depends really on what else the node might do. So here, maybe the single-thread executor might be a better choice, but maybe if the node does something else, you might want the multi-threaded one still. Okay, then let's get on to the last topic. I think we're running out of time, but I will try to be very quick about this. So deadlocks is something that can happen if you set the callback groups with somehow incorrectly with the application, and this is something that is really annoying, and it can really ruin your system, because something just suddenly stops working and it's not responding anymore, but it doesn't necessarily cause a crash. So so if we take a look at let's get back to the file processing side of things. There's timed file processing.py, and if we take a look at this file, it has a again clients to the image and video processing. Now this name we had changed, so let's change it here also. And then it has a timer which is running, calling both of these services at once. And yeah, so it should be repeatedly in 5-second intervals calling these again and again. So let us see how this will work. Let's run the file processor. And on the second terminal, let's run this timed processing. If I can find the second terminal. So we wait for a couple of seconds for it to start. And now we got the, okay, this time the video processing works. Yay. Not sure what was wrong with it before. So now it started working, which is good, but it looks like we only are sending in the request to videos, and the timer kind of gets stuck. We don't get any more calls than that. So let's stop this and think about what went wrong. So what went wrong here is that now in this timed processing.py, we're also running the node in a multi-threaded executor, but because we've not set any callback groups, all of these timer and the clients are in the same mutually exclusive group. And now, because we're using synchronous calls here, we would want to wait for the call to finish before sending a new one. What happens is that in order to get the result for this service, you will need to run a done callback for it. But because this timer callback is running and in the same group as the client, it blocks the execution of this done callback and causes the whole node to stall. And then it also prevents this timer callback from finishing, and so it cannot fire again anymore. And the solution is to separate this timer to a separate callback group so that this timer callback can run freely or these done callbacks can run freely of the timer callback. And what should then happen is that you get the result here from the video processing, and then the image processing can start. And once that finishes, the whole timer finishes, and we get the results, and the timer can fire again. So let's again import the callback group, and this time we just want to add it for the definition of the timer. So add it here, and let's rerun. So 5 seconds, videos processed, and images processed, and finished, and timer's firing again. So that fixed it. Now it's working as supposed to, and we're getting the backups or whatever we wanted to do with these timed calls. All right. So then onwards to the very last example. This one uses Turtlebot simulation, so let's get that fired up right away. There is a ready-made launch script for that, so just copy these two files in a new terminal and run them, and let's hope that this works as expected. And then let's start investigating what we want to do. Sorry?
No, sorry. Some problem with the mic here. Sorry.
Okay.
So keep going.
Yeah, I'll try to finish this really quickly. I know we're a little bit over time already. Okay. Yeah, so let's inspect the new node that we have. Back to the object storage package, and we have an object navigator.py. And this is now a little bit more complicated looking node already. So we have essentially 3 entities here. We have a client for getting objects from the object handler. Then we have an action client for calling nav2's navigate to pose to move the robot. And then we have an action server which combines these two into an action for navigating to an object. So this is so that you can just give it an ID of an object and it will get the location of that and have the robot navigate to it. So brief code inspection will tell you that the execute callback is just that we get the coordinates from the object handler and then we navigate to them by calling nav2. And because this is a navigation action, it's a good practice to have it be cancelable. So we have implemented the canceling here so that if the user requests cancel, we relay that forward to the navigation. And if the navigation returns that, okay, all okay, we're canceling, then we accept the cancel back to the caller. And otherwise we reject because we don't want to get like promise something that we can't do. So here's how this works. I think we will need one more terminal maybe for this one. Let's get the previous ones here. Okay, I'll get one more just in case. So let's run all of these things. Let's first of all source anything that wasn't sourced yet. So this one, and then we want to run the object handler node in one terminal. I'll make that a little bit smaller. Doesn't need to be that big. And then we want to run the object navigator in a second. And the last one we will use to give the action call. So I think it's this one. Let's have it here somewhere, kind of visible. So let's keep that, and let's also try and find our simulation and this is not. Okay, it's there. Nice. Can also see what the robot sees. All right, let's send the call, see what happens. So we're going now to object number 3, which is somewhere here at the top of the file, and looks like it started going as expected. The robot is moving, and let's see what happens when it reaches the goal. We got a message that it's done, and yeah, so everything seems to be good. Let's still test the canceling. So let's navigate to another object, let's say number 1, which should be at the bottom of the map, and let's cancel the movement of the robot when it gets moving. So now it started moving. So let's cancel here. Didn't cancel. So something seems to be off. Okay, well, let's let it finish. What actually is supposed to happen is that it's supposed to. Let's try it again. Let's go back to number 3 and give this a second try. So here and cancel. Okay, now the robot did stop. But if we look here, we didn't get this done message. We just get the message about why the navigation is now canceling. That it's canceling and the robot stops, but seems like the action doesn't quite finish. Now if we try navigating again to this same, then nothing happens. We don't even get the message about starting the whole task. So something is off, and the canceling doesn't seem to work as expected. And here is why. Again, we have not set any callback groups. And while the execute callback doesn't care about the callback group restrictions, canceling an action is a regular service.
We are running out of time.
Yeah, I will 2 minutes.
Oh, okay.
1 minute. 1 minute. Yeah, I will be very quick. So canceling is a regular service, and because this action server is in the same group as the client, then this client, when it relays the cancel request to navigation, it will need to run a done callback for that service, cancel service, but it gets blocked by the servers cancel callback, and that then causes deadlock that prevents also getting any new calls, because the callback of a server action is also a regular service. So how do we fix this? Well, basically just separate the two action entities to different callback groups. And here we've chosen to separate the client. What this should do is that the client's cancel and result callback should be able to run without being hindered by the server's callbacks, and that should fix it. So again, for the last time, let's import the mutually exclusive group and add it to the definition of the action client. So here. And let's run again. So I think we'll need to find where we had the this is the one where we had the object navigator. Rerun that. And let's give a new goal. Let's check where the robot is. So let's go back to the object number 3. And again, let's cancel when the robot gets moving. Now we got the done message and the robot stopped. And if we send a new goal, the robot continues. So indeed, it looks like changing the callback group fixed the deadlock. And that is all I had for you today. In conclusion, you should really care about callback group if you are working with any kind of multi-threaded executors. And well, then there was some problem with the examples, but I'm not sure what's really up with that. Okay. Let's
don't
stop
worry,
now. We are
Taneli, it was very clear, and also the good thing is that the audience, they did it, make it work. So something is strange in this.
Yeah, something is strange in this virtual environment, and this is not the first time that I see it. I'm not sure what's up with it, but okay, that's all that I had planned.
Okay, excellent. Thank you very much, Taneli. Thank you.
Thank you, Taneli. So now let's start the Q&A section. Attendees, please post your question in the Q&A tab or vote for questions posted by others, and we will pick the most voted question to ask the speaker. Okay.
Yes, and then there are already some questions for you, and here already. And one question from Rodrigo Gonzalez that says, how would you decide whether to use callback groups or multiple threads?
Well, I'm not quite sure what the question is asking, because the callback groups is something that you really only need to concern yourself with when you are using a multi-threaded executor. So if you are using a single-threaded executor, then you don't need to worry about callback groups, because it's essentially like everything is always running in the same mutually exclusive group. So I'm not really sure what the question is, but I think it might basically, I think you should decide whether to use a multi-threaded executor or a single-threaded one based on what the node does. So if you have some kind of chaining of services or something where you need the result of one service in order to complete the second, then you for sure will need to use a multi-threaded executor and also care about the callback groups. But if your node is doing something very simple, it's just it gets a message and it processes something, it then relays it forward to a different topic, then probably you won't need even a multi-threaded executor. And then you don't need to care about all of this stuff at all. Okay. So it really depends on a node by node basis what your node does.
Okay. Then what about the question from Alberto that says, in general terms, would you advise to use mutually exclusive callback groups when working with several callbacks for a better control over them?
This is again something that I think kind of depends on what you're doing. I think, or what the node does, what it's handling. In general, I try to approach it in such a way that I prefer to use mutually exclusive group rather than reentrant ones. Whenever I don't have to allow something to like execute multiple times on its own. So I myself prefer usually to go with mutually exclusive groups, but there are certainly cases where that's not enough, though I find those to be actually quite rare.
So we can answer that it's on a case by case basis, right?
Yeah, this is again. I think most of these things are a case by case basis. I think it's better practice to use multiple mutually exclusive groups than one reentrant one in most cases, but there are exceptions for sure.
Okay, maybe I think that this is material for a paper or an article.
I think that would be a whole different lecture. Design when is best in which cases, or a series of lectures.
Okay. Some ideas. We are launching some ideas. Okay, we have more questions on the chat, but we don't have more time. Then thank you very much for the hard work preparing this. I can tell you the notebook of Taneli is pure gold. Despite the problems that we had, you have to check carefully the images included there because they are going to clarify you this subject. Really. So thank you very much, Taneli, for putting this together. Thank you.
Thanks.
Thank you, Taneli. Okay, bye-bye.
Bye.
Okay, attendees, so now you will see a small box where you can rate the speaker. Please take a moment to rate this excellent speech by Taneli, because at the end of the conference, we are going to announce the best speaker of this ROS Developers Day.
Yeah, and now, so what do we have now? So we have to go to the next speaker, right?
So we need to get the next ROS chat open.
Okay, yeah. So you can see now the ROS chat that is appearing on the button, maybe on the Docs tab or here underneath this video. Maybe it depends on which screen you are. Check it and it says open this talk ROS chat. You can click it and start preparing for the next speaker.
Yeah, great. So while the next speaker is getting ready, let's have some fun again.
Yes.
Now let's have a prize quiz. So the winner is going to get an ROS Developer T-shirts, yes, and a coffee mug, sponsored by Robotics Automation, a leading company of industrial mobile robots and manipulators based on ROS.
Yeah, and then how does it work? This game in which you can win this is we are going to put a video about the sponsor, and then at the end of the video you are going to see a question that you can answer by watching the video. The first person that correctly answers the question on the chat will win the T-shirt and the mug.
Yeah.
Okay, so let's go. Let's watch a video. In the meantime, the next speaker is getting ready to get into the presentation, and see you in a few minutes.
See ya.